So let's get into binding energy. And binding energy is basically the energy required to basically separate the nucleus into its components. In nuclear transformations, such as fission and fusion, there is a mass defect that occurs, or mass is directly converted to energy. And so we find that we could look at, a change in energy is really looking at a change in mass times the speed of light squared. So we have c, which is our speed of light. We could say that's 3.0 times 10 to the 8th meters per second. We have here really looking at the mass defect, meaning the mass of our starting materials minus the mass of our product. We want this to be in terms of kilograms. And then we have our binding energy. That is now looking at, how much is being released within this process. And so we'll have that in terms of, kilojoules per mole. So a couple other features that we have with this expression. We might remember atomic mass units. One atomic mass unit is equal to 1.66 054 times 10 to the negative 28th kilograms. 1 AMU is also equal to 931 mega electron volts. Hopefully still remember that our 1 mole is 6.022 times 10 to the 23rd particles. And that 1 mega electron volt is 1.602 times 10 to the negative 16th kilojoules. So whenever we're trying to figure out binding energy, this is the expression that we actually need to use. So let's look at an example of this. Conversion or or energy that is produced by the following nuclear reaction. And so the masses that we have here for the boron 10, we have a mass equal to 10.01294 AMUs. For our helium, 4.00260 AMUs. For the carbon is 13.00335 AMUs, and for the hydrogen equal to 1.00783 AMUs. So when we're looking at this, notion of, binding energy conversion, or energy is produced from the following nuclear reaction, right? We're looking at, this expression. So the first step here would be really to get at our energy in terms of first getting at our delta M. And then we can get to our energy, but realize that that's going to be in an energy per particle unit. So there has to be a third step, which is then a conversion to get this into terms of an actual energy of kilojoules per mole. So for our change in mass, we just want to take the differences of, the sum of the masses of the starting materials minus the sum of the mass for the products. And so our delta M here would be equal to 13.0035 plus, that's our product. Let's get our starting material. That would be the boron, the 10.01294 plus the helium minus then those products, which would be the carbon with the 13, and then the hydrogen at the end. And so we end up with a change in mass equal to 0.00436 AMUs. So now we need AMU to get to kilograms. Because remember, a joule is a kilogram meter squared per second squared. So we need to do that conversion here. We have that conversion above that. That's equal to 1.66054 times 10 to the negative 27th kilograms. As far as our AMU unit conversion. And so we end up with a mass equal to 7.2399 times 10 to the negative 30th kilograms. Really not that much of a change. So there was our step one, getting our mass. Step two, now we can plug that into our expression and solve for the energy. And when we solve that, we get a change in energy equal to 6.5159 times 10 to the negative 13th. And that would be in terms of joules per atom. And our third step would be, the kind of the final conversion to get to the desired units, where we have here, our 6.5159 times 10 to the negative 13th joules per atom. There's 6.022 times 10 to the 23rd atoms per mole. So getting out of the atom unit, getting into per mole, and then there's 1,000 joules for every 1 kilojoule. And so now in terms of kilojoules per mole, and we end up with a value of 3.923 times 10 to the 8th kilojoules per mole will be released upon this nuclear reaction. Occurring. So that's where these large magnitudes of energy come from, as far as looking at, nuclear processes such as fission, where we're looking at, something on planet Earth like nuclear power plants or nuclear, bombs, as well as then on the fusion side of thing with like the powering of the sun. It all comes from this idea of mass defect and binding energy, and how in these reactions that there is a mass defect or a loss of mass, and that mass is converted directly into energy, and actually great quantities of energy. So the two different types of, major nuclear processes are fission and fusion. And one of these we can do on planet Earth and one we can't. So fission we can actually do on planet Earth. And so fissionable isotopes are highly unstable and split into two smaller isotopes, as well as producing radioactive particles and lots of heat and energy. Right? And so this is what we're talking about in terms of, a nuclear explosion, where, us using it as a power source. So this basically occurs with these really fissionable isotopes, and that's always, the problem with the world today is getting your hands on fissionable material. So you can start with basically a non-fissionable isotope, and with neutron bombardment, you can generate a fissionable isotope. And this entity has a lot of energy, and goes on to produce smaller isotopes, radioactive particles, energy. A lot of energy is actually produced. And so it's access to these, isotopes that's holding, countries back as far as becoming, a nuclear power. In order to become a nuclear power, you have to be able to obtain enough of this non-fissionable isotope. You have to really purify it away from a lot of other isotopes that actually exist for the element. The big player on the field these days is uranium-235. Because if you take uranium-235 and you undergo this idea of neutron bombardment, you basically make uranium-236, and this isotope is fissionable. So, the ability to isolate this isotope makes you a nuclear power. And that's the whole big deal with Iran and other countries that are involved in trying to do this, so trying to get more uranium-235, which becomes fissionable, and now you can use it, for good practices, such as nuclear power plants, supplying power to the people, etc., but also for devastating consequences as well. And so then this uranium reacts, and the problem is that it's very unpredictable what you're going to get. Maybe one element of the uranium-236 turns into rubidium-90 and cesium-144, as well as producing neutrons and heat, or another completely complementary process. And really we should say, and or going to bromine 87 and lanthanum 146. And so that process, we would produce not only heat, but now 3 neutrons. as well as then a third possibility of zinc 72 being formed, and samarium 160. In this case now 4 neutrons plus heat. So the products are impossible to predict. And all are basically valid. So not only do we get the heat produced from that, but then we also have, then decay processes that still occur, meaning that the products of this fission reaction are radioactive, right? Harmful to biology. And they're existing for quite a while. We could look at, for instance, that first product, rubidium 90. It actually can turn into strontium 90 by way of beta emission or beta decay, and we find we have a half-life of that of 2.8 minutes. So it's pumping out beta particles. That strontium 90 actually isn't terribly stable, and it turns into yttrium 90 as well as ejecting beta particles. Though that process is a little bit longer, it takes 29 years for half of the strontium to decay. And then we go to the yttrium, and it can continue down the process to zirconium. So all these have different half-lives, how long it takes for half the material to disappear. But the problem with the nuclear reaction is not only do you get the energy and, the heat, right, from a very, very small amount of material, but then you also have this radioactive decay that's existing for quite a long time. So you have pros and cons as far as nuclear energy, right? We can get a lot of it from basically a very small quantity of material. Wow. Right? The cons is that all these, product isotopes are radioactive. And detrimental to biology and have significant lifetimes. So, good and bad. But that's the idea of how we use nuclear power in terms of a fission reaction, or in terms of destructive power, in terms of a nuclear weapon. In terms of your nuclear power plant, cartoon here, it's basically just a big steam engine. Where you could imagine, and this is a very crude representation, people, so please keep this in mind. Where you have this vessel, if you will, and we could say that it has water in it. Sometimes they use deuterated water as well. And within this water environment is basically a box where we have our nuclear reaction. And so it's giving off heat and energy. We place within it the ability to control the nuclear reaction by what we call carbon rods. So these species that look like this are carbon rods. And they absorb the neutrons being produced. But we have to realize that this is a cascade reaction, meaning that one uranium-236 is going to undergo fission, and in doing that is giving off neutrons, which is going to cause the formation of other uranium-236s. And so it just gets exponential as far as how many of these now you can activate. Because if you look back to our reaction, in one reaction we gave off 2 neutrons, in another one we gave off 4 neutrons. So this is what they call a cascade. And this is what you can't let get out of control. Or basically you have a nuclear meltdown. Such as in Chernobyl and Fukushima. So that creates superheated steam. And the superheated steam gets pushed through our opening here, and basically we come across sorry, that cartoon's horrible. Come across an area where it passes through a turbine. And we have that, with copper wire. That's where we get our electricity. And so the steam basically pushes the turbine in the direction, gets it moving, and then passes out the other side. And that is where we then see basically the big caricature, representation of the nuclear power plant, which are those big, great steam vents. And so that's where all the steam then actually comes out. So there's our really cartoonish representation of a nuclear power plant and how we can use nuclear reactions for power. Obviously, the box that contains a nuclear reaction also contains all those radioactive isotopes, and that's where nuclear waste actually comes from. There's also the idea of fusion. And this is what happens basically on the sun. And so here we're looking at now a combining of small isotopes to make larger ones. And there's, a vast array of fusion reactions that are going on in the sun. It takes a lot of gravity for this fusing of two elements to occur, or two isotopes to occur. So you could look at, for instance, like I said, there's a myriad of processes that are going on in the sun. But you could look at, protons. They do call it kind of this proton soup. A really hydrogen atom. That's, getting fused together to produce deuterium, as far as producing as well a positron particle. That deuterium could go further in reacting with another hydrogen atom and fusing to produce an isotope of helium. And then even another process, continuing down kind of that cascade, reacting with yet another hydrogen atom to produce helium or alpha particle. Right, and all of these have energy associated with it. If we were to combine these, we would have roughly 2.38 times 10 to the 9th kilojoules per mole produced with this particular process of fusion, just with these reactions I've shown you here. So a lot of energy is actually produced with these processes. And if we were to kind of compare the two, say, the amount of energy produced is basically equal with the following amounts of material in a given process. So let's expand on that, meaning that the amount of energy that we would get, let's say if we were combusting coal. So looking at a combustion reaction of coal, we could produce the same amount of energy if we burned 186,000 tons. It is the same energy as then a fission reaction with uranium-236 as using 92 grams of uranium. So we get the same amount of energy by combusting 92 grams of uranium. I could actually hold that in my hand, compared to 186,000 tons of coal. So there's the big draw in energy and that nuclear game, and then amount of waste at the end, compared to a fusion reaction where we would be, producing helium. We would be producing only 4 grams of helium. So this is a huge, big difference in terms of energetics, even going from the fission level to the fusion level. It takes a lot less material in terms of mass, even though, we're looking at things that are much, much, much lighter, right? So that's where that mass change is actually really occurring. But both the fission process and the fusion process, producing about the same amount of energy. So just to look at that in terms of, just a reaction standpoint, we could look at, let's say, the combustion of hydrogen gas. To produce H2O. We could say that there's an enthalpy for that process equal to negative 284 kilojoules per mole. We can then go to a nuclear reaction where we're looking at, this uranium-236 going on to, a myriad of decomposition products. The delta H of reaction for that process would be more like negative 3.2 times 10 to the 10th kilojoules per mole. 10 to the 10th. And then if we get to our, nuclear reaction, but now being specific to fusion, where we're looking at, 2 hydrogen atoms and neutrons. Like I said, there's lots of processes that go on within that sun. We end up with a delta H of reaction equal to negative 3.7 times 10 to the 10th kilojoules per mole. So again, just trying to show you the amount of energy that's actually produced is huge with these huge, as we say, in the Trump era, compared to the actual combustion reaction process. So, and now let's look at the kinetics of radioactivity. And so remember that these reactions are always first order. So we have those two expressions as far as half-life and our linear fit. And we've actually done kinetics already, in prior sections. So this should be really a review. I'm just going to go through an example really quick here. But these are always first order. There's no question about it. So here, bismuth 210, which has a mass of 209.98 grams per mole, is a beta emitter, meaning each bismuth 210 emits one beta particle. And it has a half-life of 5 days. If 1.2 grams of the bismuth 210 has been left exposing a plant for 13.5 days, has been left out. How many beta emissions would the plant be exposed to? So there is our question. So again, seeing that notion of, okay, we have a beta emitter, we're talking about radioactivity, we see the notion of half-life as well, and so that's immediately pointing us to, this idea of first order expressions. So we have our half-life expression, and we have our linear fit. And we have a couple of different values in going through this. We do know our half-life is of 5 days. And we know that we have a time as well, which is 13.5 days. We also have an original value, or n sub naught, which is 1.2 grams. So if you look at the equations, we have a couple different pieces. We have our half-life. We have our original number or value. We have our time. But what we're missing is we're missing our K, and we're missing what we're trying to solve for, really, which is this value of how much is left over. We want to eventually get to n sub t, because if we take a difference of nt minus n naught, that will tell us how many bismuth 210s have, decayed. Then basically how many beta particles are produced. So we first have to really start with our value of K. That would be the first place to begin. Because once we have K, we can then plug it in and solve for n sub t. And then we could finally address the final point of getting into how many beta particles or beta emissions the plant has been exposed to. So if we start with 1, we're looking at our half-life expression. We know the half-life is 5 days. And so all we need to do is some simple algebra here and solve for our rate constant to be 0.1386 reciprocal days, or days to the minus 1. So there's step 1, getting at our little k. Step 2, we're now going to the linear fit. So we're looking at now the natural log of our bismuth at some time point, right? That's going to be the 13.5 days is equal to negative kT plus the natural log of that bismuth 210 original. And so we're solving for what we have on the left side of the expression. We have our K, right, 0.1386 reciprocal days. We have our time, which is the 13.5 days, right? They're the same unit, so we don't have to worry about changing things around. And then we have on the far end our natural log of the 1.2 grams. So if we go through that process, right, and solve for our n sub t, right, we need to take basically the base 10 of both sides. And if we do that, we would end up with our bismuth 210 now outside of the natural log, getting rid of that with E. Sorry, I think I said base 10. That would be logarithm. This is natural log, so we have to take E to the x of both sides. And so we're taking E to that product of the K times the time. And then the other natural log would disappear. And so we just have the 1.2 when we took E to both sides of the expression. And so if we do that, somewhat slowly, this would be E to the negative 1.8711 which would be equal to 0.1539 times that 1.2, or our bismuth 210 concentration or value after 13.5 days would be 0.1847 grams. And so this would be how much is left after our 13.5 days. So that is then step 2. So we know how much we ended up with, and now we actually know a difference. So now looking at taking the difference of those two values as far as our original and our 13.5 days. That's basically going to equal the change, or the amount that has decayed. So we started with 1.2 grams. We just ended up with 0.1847 grams. So we get a value of 1.0153 grams of the bismuth 210 has decayed. And so now it's really just a conversion process. Where we want to divide by its molar mass of 209.98. And then for every mole, there's 6.022 times 10 to the 23rd particles. And that conversion allows us to come to our answer. So we're getting out of mass of the bismuth 210 by dividing by the molar mass, and then getting out of moles by using Avogadro's number. And we end up with 2.912 times 10 to the 21st beta particles were emitted. And that is our final answer looking at kinetics.